Ladies and gentlemen, for one night only, Dr. Rich Mansfield.
Woo! So, can everybody hear me? No? Oh, jeez, that's good. All of a sudden. Well, thank you for turning up. So this is a pre-session before the Lustre user group. So if you expect the Lustre user group right now, you're wrong. So, I've got agenda here. We'll probably repeat this later on. So let me just concentrate on the first one there, right at the top. That's me. So, the idea of this session is basically came out of a talk with our fellow colleagues and our customers, because we wanted to provide a series of tutorials which is aimed at the end user. I think all manufacturers out there aim their courses at the administrators, but we really want to go for the end user, the people who actually consume Lustre as a part of their everyday job, as to make jobs on their supercomputer, for example. So that's why this tutorial came about. And very first of all, it's going to be aimed at new users. So a little bit of audience participation first. You can see a lot of blank faces. Right, who uses HPC per se? End users. Handful, don't be shy. Yeah, 1, 2. Who uses a file system called Lustre? 1, 2, 3, 4, 5. Not very good, is it? So, well, or alternatively, you're interested in Lustre and you want to come here to know more about it. Anyway, good, great. Thanks for that. So, let me just go quickly what the basic themes are. I'll introduce you to what is Lustre, what is Lustre file system. We have Andreas here, who is long been known as not quite the godfather of Lustre, but the maintainer of all the goodness of Lustre. We'll talk about the I/O data path. So what we mean by when you're on the command line and you submit your job, and you're your end user, how does that interact with these components, which we're going to describe? And that goes on to the second bit, what are the components of Lustre? And then introduce a topic called stripes, which is the reason why Lustre is one of the most commonly used file systems. And all the performance benefits comes out of this feature called stripes. So we give an example of what it is and how you can change that to make effectively your application go faster. And then we also thought, well, that's only one side of it. If you're sitting on the command line and you want to see what are components provisioned by your nice system administrators, and what's the capacity of each of the components and where these components are, we'll also introduce you to a couple of commands. You can browse these components. And finally, what next is, I alluded to this before, we hope this be a series of tutorials. This is the introduction, so you would then probably think there may intermediate or advanced, and there may be some other topics. So if you've got ideas how to develop this series of tutorials, please let us know. Okay. So there's a lot of text on here. I'm not going to read every single line, but to say, so what is Lustre? So Lustre is a software-defined storage. It uses common components behind there, like controllers and disks. It has some networks. But the main thing is, it's really truly hardware agnostic. So you can get components from Dell, from DDN, from HP, for example, Supermicro. And it's really what's nice about Lustre per se is that it is truly hardware agnostic. So you don't have to have lock-in. If you don't want to lock into a vendor, you don't have to. It is quite nice. It is open source. So no one person owns the source code. Everybody can contribute. Everybody can apply patches, upload patches. We're very grateful for people to actually want to develop a feature. Those would be be studied and accepted, and if possible, be accepted into the main code stream. It is a file system. It is POSIX-like. I think there's only a couple of rules, which I won't bore you to death, which makes it non-fully POSIX, but most things about Lustre is POSIX, which is what people understand most. Yes, you can have like S3, put-get architecture. You can have Hadoop or whatever, fancy other file systems out there. But most people interact with this file system via POSIX interface. And it's quite common. It's used prolifically across all of the major supercomputers out there. And historically, it has a very high adoption rate. So when you do get these slides, if you do want to click on the source code, this is the true nature of Lustre. You can download the source code if you wish. You can compile the Lustre servers if you wish, and the Lustre clients if you wish. Or if you want to, you can just download the RPMs, great, full of OneCloud. So it is really true open source. So there's no vendor lock-in. So let's just do 2 slides of compare and contrast. So what we'll compare with now is how most people think how to, oh, bless you. How most people think how quickly they can actually create a parallel file system. There's a very nice protocol out there called NFS, right? Network File System has been out there for quite a while. But fortunately, if you do have this idea to try and give your lots of users access to a shared file system which is based on NFS, there's some architectural weaknesses here, unfortunately. A lot of all these servers are scaled out, NFS for sure, but the main thing is the NFS client, which is represented at the top there, has no concept of where my data is stored. This is not parallel NFS, this is just null native NFS. So only way the client can find where the data is, it has to do the first hop to a server, which is hosting the IP address or virtual IP address onto which it mounts. But that particular server then knows where the data is, and it could be subsequently met other additional hops to actually finally get to your data. All these hops, all these extra jumps, introduce latency into the data path, and HPC hates latency, and hence your performance will go down. And it's not really scalable architecture as well. It's quite quickly can saturate. If you have thousands of clients all very, very actively trying to access these servers, it's not exactly the architecture itself is quite weak. So compare that to a parallel file system, such as Lustre. Now the main difference here is a client knows explicitly where the data is. So when the client wants to, in this case here, write to a series of servers down here, the client can write in parallel to multiple servers. So A, you break that serial nature, you're now writing in parallel, and B, the client doesn't need to look up where the data is, the client knows where the data is. So this architecture is significantly better for very large deployments. So I mentioned Lustre, Lustre parallel file system. So when you do look at Lustre, there's certain terminologies and certain names which I basically want to introduce you now and walk around this diagram. So this diagram has some storage at the top. It has a network in black. And I do apologize, the color's not very good. But you've got some network over here. Then your compute nodes sitting down here. So you see these terms talked about, and I'll go through each one of these in turn to say roughly what each one is. So let's go forward. So highlight over here in yellow, so the MGS. So MGS is the management server. So think of this as a yellow pages for the infrastructure. The management server knows about all of your components in your file system. It knows how when you introduce new servers into this architecture, it extends their capabilities. So this solely is like the brain or the heart of the cluster. It's purely talk about infrastructure. It doesn't contribute anything to the data I/O. It's merely just the knowledge of the file system. Now, these are now the next components, or the active components. So there's two main components of Lustre. I'm just talking about the metadata server. I assume we'll talk about object storage servers. So this is where the metadata server, so this maintains your file system. So where your directory path is, basically your namespace, any files, for example, reside on a metadata server, and it has optionally a series of metadata targets. These are volumes. You have multiple metadata targets inside your Lustre file system, and each one will then increase the performance of your metadata services. So if the previous one is purely metadata, as in the name of your file, the contents of that file, whether it's 1 bit or 1 gigabyte, is handled by the object storage servers. So object storage servers, like the metadata servers, has a number of object storage targets, and that's where the data, the content of your files are stored. So then you have to deliver this file system over the network. Now, like any parallel file system out there, it's a shared distributed architecture, and it relies heavily on the network. So quite nice thing about Lustre, it extracts the requirement to have a low-level knowledge of individual network architectures, such as Ethernet, such as InfiniBand, such as more complicated networks, such as maybe Cray, Aries, or OPA. You don't need to know the low-level, how each of the low-level network works. It abstracts that through something called a Lustre network functionality, and that's one reason why Lustre is extremely good and friendly to many organizations. Is you don't have to have explicit knowledge of the underlying network. So it's basically, you can manage your network purely through the single LNet. It, on its behalf, will then manage the InfiniBand or Ethernet or OPA, for example. And if you ever did wonder why you'll see references to this O2 IB0, you may think that IB0 is the first interface on the InfiniBand, but the O2 is kind of stuck. O is basically for the OFED, the Open Fabrics Enterprise Edition, and the O2, I understand from Andreas, was the second version of this function for you to implement LNet. So O2 IB is synonymous with InfiniBand. So what happens if you have a cluster solely running on InfiniBand, but later on you have a new technology? That technology may be like Cray or OPA. How can you then access or utilize different networks? Well, this is one reason why also Lustre is pretty nice to system administrators and gives you the functionality to use other technologies. So we mentioned before, LNet is an abstraction away from the low-level devices. With LNet routers, think of LNet routers as simply bridging components, similar to like a switch, but a bridged components. So you could have InfiniBand on one side, and the other side, you can introduce a new technology which may not be there when you initially purchased your supercomputer, but you want to incorporate other technologies as these are delivered. And with LNet routers, you can now bridge between InfiniBand. In this particular case, we're doing TCP over here. So TCP 0 is Ethernet. So you can have both InfiniBand and Ethernet in the same environment, all because of these Elnet routers. And it's quite nice as well. It does support if you have RDMA, which is, makes the communication between client and servers very fast. RDMA is, allows very, very fast communication between those components. If both technologies have RDA enabled, it will take benefit of that as well. And finally, some other nice features which on this diagram, not necessarily on this diagram. So multi-tenancy is a very, very hot topic at the moment. How can we create a cohort of people and split that away from the rest? So how can we share the infrastructure and not allow that information to be leaked or accessed by any other tenants? So Lustre has a nice feature. We call it multi-tenancy. Now, it's not administration multi-tenancy. If you go to AWS, you want to have a multi-tenancy as in to administer environments. What we're saying here is if you create a tenant and you have multiple tenants, it's just a way we call it multi-tenancy. We could have multiple collections of users, of computers. So in this particular case here, these are blobs or your compute clients. You collect those all together. You create a node map, a map of all those nodes, and that's basically a tenant. And at some point, you may want to say, this tenant will access this directory, and it may be off your home directory /root/root 1. But you also off your home directory, you've got home group 2, for example. But if you map root 1 within that tenant and map it to a node map, when the client mounts the file system, its root is purely that home/tenant 1. It won't see anything below its top level directory. So the idea of multi-tenancy is all about segmentation. Can I segment the network? Can I segment the namespace? So that means that you're confined into a little working area, and that's basically called a multi-tenancy, a tenant, sorry. So I mentioned about a client and the servers. I thought to kind of basically show how a client interacts with each of these components. So right here, we have a client, we have this metadata server, which basically handles metadata and the OSTs, where your data is stored. And the little numbers is basically the sequence of events. So instead, the client knows where the data is. It does explicitly know where the data is. So if a client wants to read or write to a set of OSTs in this regard, you need to find out where those OSTs are. So it first contacts the metadata server. It will know all the components out there, and when answers are in return to the client to say, yes, this is your infrastructure, which you can then access. So now the client now knows it can possibly write to multiple OSTs. And in this example, okay, it's a power 3, which is odd, but we could then possibly write to 3 OSTs in parallel. Then eventually, when it's closed, the client will close the file system, and then the last command will come back and say, yes, it's closed. So this architecture is quite nice. It's quite scalable. As you see, you can have multiple metadata servers, hundreds of thousands of clients, and tens of OSTs. It's very nice, true parallel architecture. So what is striping? So we mentioned before. So Lustre is an open source project. It's adopted by lots of organizations. And one reason why it's adopted by lots of organizations is the speed it can provide to your applications. And it does this by something called striping, file striping. So on the right-hand side here, you'll see the client has a concept of a file. So you have a start point and end point, and it may be, say, 4 megabytes in total. Now, how Lustre benefits to increase the speed is through parallelism. So in a basic way, if you say this file can be segmented into smaller objects, and each object is called a stripe, and those stripes will rely on a OST. Now you actually have the ability to actually read and write many objects at the same time, and hence why your Lustre is very fast in terms of fast in terms of reading and writing, because you've got this natural parallelism in this architecture. But we'll go to the next slide. So stripes. So you think that's probably the be-all and end-all of stripes, but there's multiple things you can actually then start thinking about. How many of these objects, how many stripe counts do I want to put on? What's the size of these stripes count? So by default, Lustre will have a stripe count of 1. That means when you write a file, it will write 1 megabyte chunks onto one OST, and the second 1 megabyte chunk will go on the same OST. So the stripe size is how wide you want to write each of these Lustre stripes. The stripe count is how many, as the file goes from 0 to, say, 2 megabytes, first 1 megabyte will go to the first OST, the second object will go to the second OST. The stripe index is a bit strange. We'll skip over that one for the moment. We also have another option called the stripe pools, which is effectively, where do you want to put my objects? What I mean about here is, I'll describe it later on. You may want to put some objects on OSTs which relies on SSDs, and you may want to put some objects on the hard drives. So you can actually confine where your stripes are written to, if you wish. So I mentioned down here, so by default, it's only by default, the Lustre file system will have a stripe count of 1 and a stripe size of 1 megabyte. That's generally how you want to set the file system up, because there's other nice features which we can change. If you have an application and it has a certain characteristics, you write into the Lustre file system, and you want to increase the performance, this is the place you want to concentrate on, finding out your I/O characteristics of your application and exploiting the fact you have multiple OSTs and how many OSTs you want to write into. So you would think, if you have maybe 8 OSTs, the simplest way to get greater performance is to put your stripe count of 8, which is utilized in all 8 OSTs, and let's keep the stripe size as 1 megabyte. You may find your application will have a slight performance increase, but we're using 8 OSTs, but I would strongly recommend you to profile your application, because you may not necessarily get the benefits of all the performance by using all the OSTs. In fact, if you do look at your I/O profile and go from 1 to 2 to 4 to 8 to 16, for example, of stripe count, there is some point where your I/O will benefit from a certain number of OSTs, and this is very much user and application dependent. And we strongly encourage you to profile your application, because it's just so easy to think more OSTs equals more performance. It is, however, there's always a limitation. The limitation is, down here, it may not be the best choice to use all your OSTs. And certainly, here be dragons, please test your application beforehand. So we mentioned before, let's have a look at graphically what we talk about in terms of file striping. So we have a series of OSTs over here, 1, 2, 3, and 4, for example. And these colors aren't great. These colors are actually completely disastrously wrong. So I do believe this one here, file A, one stripe defaults, will all of file A, which is pink and blue down here, if you don't do any striping and use a standard default file system, file parameters, your file, or 3 megabytes in total, first chunk, second chunk, and third chunk will reside on the one OST. That may be not. So that may be what you want, but may not get the benefits of the parallelism of Lustre. The second one down here is going completely wrong color for 2 stripes. The red one is actually down here, OC0 and OC1. Now we were saying you're keeping the same stripe size, but we've got stripe count as 2. So the first time we write to OST1, OC0, when we go above that boundary from the 1 megabyte to 2 megabytes, it'll go into OST1, and then 2, 3, 4. So this will in total be 5 megabytes. So now we've got 2 OSTs participating in this I/O. Hence, hopefully increase the performance. You can go a little bit more exotic as well down here. We'll describe this later on. So you can also not only choose how many OSTs you want to use over and the width of each of these stripes, but you can do some other weird things which we'll talk about later on. So this one here, the final one, first chunk is on this OST, and the second and third chunk is on OST1, and then the third chunk and fourth is on OST1 and 2. Now, we'll describe this in a moment, and this is basically called a composite layout. It'll probably become obvious when we talk about it in a moment. But let's talk about one thing about OST pools. So yes, each of these OSTs, go back to one, each OSTs are equal. They have a certain capacity and a certain number. But OST1 and OST2, or 0 and 1, may be on SSDs. And OST2 and 3 could be on, for example, on hard drives. So in modern file systems, we can have and exploit these different types of device media because each one has different characteristics. And hard drives aren't dead. Hard drives are very relatively inexpensive and very, very good for sequential I/O. So if you've got lots of data, and the data may be infrequently accessed, but you've got a lot of reference data, as in tens of gigabytes of data, they are more beneficial to put on spinning media hard drives. And sequential I/O happens quite nicely on hard drives. However, if your application is I/O bound, as in does lots of I/Os, or needs higher bandwidth, and then your application may benefit to reside on SSDs. Now, if you have in a file system both devices of SSDs and hard drives, how can you replace your data on the relevant media to take benefit of your application? We do that using OST pools. So this little graphic over here, and I apologize, it's not the best graphic, but what we showed over here is at some point in your directory path, if you reside in your folder and you want to put a stripe characteristic, at this point, you can say all the files in this directory will be consumed by the slow pool. This slow pool is a slow pool of hard drives. And you hope your system administrator will take all of the hard drives, create a pool, and give it a name which is more consumable, hence, maybe slow or hard drive or archive, for example. At the same time, your administrator will then collate all your SD media together on your OSTs and create, say, a fast or IOPS bound or whatever, scratch. And people will write into a pool which is named fast, will get a different performance characteristic. So if you then specify the stripe characteristic to write into your slow pool, you could, using Lustre, everything inside this directory will inherit from the slow pool, but at some other file or an other directory, you can say this particular folder will write into these OSTs, happens to be on SSD media. So most modern architectures, from Lustre, you got a question? It is, absolutely, yes, yes. And hence why they've given some name. So the name could be, hopefully, symptomatic of what you expect. Fast or slow, or archive, or if it's called pool 0, pool 1. There isn't, but it's kind of weird. It's a bad idea, and yes, so SSDs are more expensive than hard drives as well. So you're very, it's very much dependent on your application, but for sure, yes. Yes, you want to make sure that you actually, utilize pools, utilize stripes. Andreas, you got a question?
No, I was just going to say, I mean, the creation of the pools is up to the administrator, but the users can specify which ones to use, right?
Yeah. I don't think many file systems only has a single device type. Most have a notion of a fast pool and a slow pool. Unless you're completely I/O bound, then you just do SSDs. So let's go back to that other example. We talked about the striping. We talked about composite layout, where we had these different parts of stripes on different components. So as a composite file layout, there's extremely important part of Lustre. There's lots of nice component artifacts of the composite file layout. In particular, we're going to talk about in a moment. It's called progressive file layout. But while I'm here, I'll just mention there's also something called file level redundancy. Now, this allows you to actually, each of those stripes, you can put a stripe on the same stripe and create two replica objects on two different OSTs. You think, why do you do that? Well, you may want to increase the variability of reads. Your stripe is on two OSTs, both exactly the same, but your read is now doubled. If you lose an OST, then you have access to another object on a different surviving OST. So we're not talking about file level redundancy, but it's a very good function of Lustre. But progressive file layout, this for sure allows Lustre to be a lot more consumable by the common users. So what do we mean by this? So hopefully your administrator will set up a progressive file layout. However, you can also set up your own progressive file layout. So generally, I heard Sanger guys, where's James? James, over there. They really use progressive file layout to take the mysterious nature of what stripe characteristics we want to apply away from the users. But the users can override it if they wish. So this is the default mechanism. So this really is an important part of Lustre. So I say, why is it good, or what is it? It allows each. So if you, for example, write in your file and you roughly know the file is going to grow over time, and you may, for example, on the first part of your file, have an index. Think of like a TOR file. We've got an index on the front, and applications go read that bit of index on the front of your file, maybe first 1 megabyte, and that's going to be highly IOPT bound. As your file then grows, you may say, so this bit here, maybe on the first section here, maybe on put onto a media which benefits high IOPS. So this could be preferably put on SSDs. As your file then grows, you may want to increase the number of files, your file counts you have up to a certain size, like maybe in this case 16 gigabytes, and these may also reside on hard drive, for example, because your index is on the first bit, but as a file grows, you'll put these next bits on hard drives. At a certain point, you've profiled your application, and you're now really concentrating solely on streaming I/O. So now you want to increase the size of your stripe. So each one of these is called an extent. So each extent can have a different stripe count, a location, and a size. So for this one, you have first bit on SSDs, second bit on hard drives. When it goes above a certain size, to the end of file, you increase the number of OSTs, you increase the number of stripe size, and it really kind of benefits reading large files, or if you're only small files. For example, if you've only got a 4K file or 6.4K file, that will solely reside on SSDs in this example. So this really makes striping much easier for the user not to think about the I/O profile, but we encourage them to think about it if they wish. If they do, they can override, set their own PFL. So this is an example a bit more complicated using a progressive file layout. For say, for example, your home file system, so root file system called /Lustre, and for example, your home. When you actually write into the home directory and all the users are back over here, the first 64K of a file could be confined to your flash pool. So they benefit from the high IOPS which flash provides. But as you increase above 64K, this parameter it can be configured differently. To the end of file, we'll say, okay, from 64K to the end of file, the rest are going to a hard drive. If you want to purely IOPS bound, if you write into the IOPS directory and your system administrator sets the PFL for IOPS, you'll say every file from 0 to the end of file, all we're going to your flash pool. So now you've got a difference that some files will be on flash, and some files will be on hard drive, or some components will be on hard drives, but these solely on flash. But this one here, the data sets, is quite interesting. A lot of applications out there require some reference data, whether it's life science or automotive, but you need to have reference data. So reference data for here, these files could be quite big. You don't want these files to reside on expensive SSDs, and especially if these are large files, commonly there'd be sequential I/O commonly. So you now can set this /data set to, as a file grows, you say, first 1 gigabyte of file will be one stripe. As it grows larger, from 1 gig to 10 gig, we increase the stripe count to 2. As it grows again, greater than 10 gigabytes to the end of file, we can then increase that stripe count to 4. And all those components will be on hard drives. So yes, hopefully your friendly system administrator will set this up for you, but yes, you can also override this and do a similar mechanism. So this could be your home directory, this could be your output directory, and this could be your reference data directory. And you can control all of these features where the data is placed onto the right media for your application. So some examples. I think talk with Lustre will benefit, will happen if you don't have a command line option. So how do we set these stripes? Well, most features rely on this LFS command. A lot of functions you can use LFS. We'll show later on how you can quiz what each of the components are from your file system. But the main thing is set stripe. So one we're talking about here is set stripe. So set stripe, for example, in this example, we want to create a stripe count of 4 using the default file system default stripe size of 1 megabyte. If you don't change that, it'll be 1 megabyte. So if we do set stripe count 4 of my file A, at this point, your file is not created. So you have to, before you create the file, you have to tell the Lustre what layout we want to provide. When we start writing into this file, we can do the counterpart of setStripe, which is getStripe. So getStripe this file A, and we can now see that it's been iterated through 4 OSTs because we had a stripe count of 4. This is a 1 megabyte size. So it happened to be that when the file was created, it started on index of 5 and then went through an index of 6, 7, and 8. So we can see that this file is striped over 4 OSTs, and each of these objects, these stripe, has a size of 1 megabyte. But that's the only thing you can do. You can also increase the stripe size, because you may know that you're doing sequential I/O. 1 megabyte may be not big enough. So you can actually say, for this example, I want to do a stripe count of 1, because you've worked out that you're not dependent on number of OSTs, but I want to write quite a large file. So the stripe size of 4 megabytes on the same file B. Now it's a similar output, but stripe count of 1, but each stripe in its size solely relies on, this case, OST 7, and each object of size stripe on OST 7 is of size 4 megabytes. So we encourage users to actually use LFS set stripe with the intention to actually know the application and choose the right I/O characteristic which benefits their application to utilize each of the OSTs. The more complicated version of that, this is where we go into the progressive file layout. It may look quite daunting, but what each one is the same. It's the same method we said before about the set stripe. But what we're doing now, we're doing maybe 3 stripes layouts onto each file, and each of these layouts is called an extent. So if you prefix the command with the -e, it means until the next e, everything in between these 2 e's is the extent. So we say on here, the component 1 down here. So we say for a count of stripe count of 1, each one of these files objects will be on a single OST, and each one will be 4 megabytes in total, which we have. When they go to the 5th object, we now increase the stripe width from 4 megabytes to 64 megabytes. Hence, we demonstrate it by having a larger chunk. And now we've got a count of 4. So the second extent, as the file grows in size, will now be striped over 4 OSTs. Then finally, at the end, the -1. I was slightly wrong here. Andres, help me out. Yes, but I thought the count is -1 here. Yeah. So So this one, So now we are writing sufficiently large files that will take benefit of all the OSTs. So this is quite a complicated example, but your sysadmin, friendly sysadmin can set these up for your directory, and hopefully they capture all. But bear in mind, you can also override it. So you're sitting there with your flashing cursor, and you think like, so what have I got then? So I've got the mount point, I can see DF, I can see DF and see I've got my /Lustre mounted. But how do I identify these things as a user, not the sysadministrator, as a user? So this LFS command also has other many different options, but 2 options we show here is an OST and MDTs. So LFS OSTs simply lists each of the OSTs you have, but it doesn't say down here if each of these OSTs are what device type. So these may be, first 8 could be SSDs, and the other ones could be SSDs. You'll have to use pools, and hopefully the name of your admin will set the pools up to find out, to utilize these. But you can see this, the number of OSTs, because you want to know how many to use. If you say stripe count of 4, that's fine. Stripe count of 16, you have a problem because you haven't got 16 OSTs. And it also says that active or not. So if you do have an issue and you see your I/O is stalled and you want to find out why, there's many reasons why, for example. But if you think your OST is inactive, this active component here will show that this is a good clean state. We want to see everything to be active. Likewise, for the metadata targets, I haven't talked about how we can utilize metadata targets because that's kind of more of an advanced topic. But you also can show and list how many metadata targets in your file system. In this example, we've got 4 metadata targets. So previously, we got a list of OSTs, which means nothing to the user other than how many OSTs I can actually utilize. But we also can list how many pools we have. So in this particular case, again, the sysadmin hasn't done a really good job over here, but we've got a notion of SSD. So this DDN_SSD pool, we hope that here we go, on the right-hand side. So we listed on what pools we have, and we say you've taken this name over here, then do lctl, okay, it's the second command, beg pardon, but lctl pool list, and give it the name, and now we can say, show that these first 8 OSTs are associated with this pool. We hope the admin gives it something sensible to actually, well, I know, that's why you did it, but why did that one there? Yeah, maybe. But see, this name of the pool means nothing to me and you as a consumer. What is this? Hard drive, SSD? We don't know. So hopefully this SSD here will give it a name. Which one? Well, it's a particular case, yes. But at least we can take this name and find out what each of these OSTs, and hopefully these are grouped together with the similar characteristics. In this case, would be SSDs given by the name. You also, when you do DF, you will find your usage, your consume, how your standard way, how much this is consumed by the entire file system. But you also want to, because each of the OSTs has a certain capacity. So if you do LFS DF, it's like exactly your DF command. You see down here your metadata targets. These will probably consume less. This is typical because metadata targets only needs to store in the basic form. Only needs to store an inode related to where my file is in my name path. So the usage is probably quite low on your metadata targets. This is quite common. So then we go through your OSTs. So this one here has got some, 8 OSTs of 20% usage, and then we've got some more OSTs of less. So each one of these, you can do LFSDF and find out the capacity of each one of the OSTs. And if you do see one particular high, like 80% or 90%, and you have a control, why would you want to put data onto OST which is higher? So you can actually, perhaps skip over the OST. Again, this is, user configurable. Like DF as well, DF will come back, do, I think it's in blocks by default, isn't it? If DF brings how many blocks you use back. You can do a DF -H and make it human readable. So instead of going back up to here, how many blocks you got available, 1K blocks, you can say DFH and it's more consumable. So this case is 2.8 terabyte each of these OSTs. And in total, this 619 is summation of all the OSTs above. So as a user, we mentioned before about this LFS get stripe. So let's have a look what we have. So you're in this directory path here, and again, apologies for the path name, but you can just about see it over here. This is my good colleague Vic provided this. So we're on a file system. We own Vic's home account, and do LFS get stripe -d dot means myself. And you can see if Vic writes into this directory, it will have one count each size with 1 megabyte, and the -1 means it will write over each of the OSTs, and it's on the hard drive pool, which is over here. So it's quite a nice way to actually confirm what you're seeing. Now the next one is slightly more complicated, but quite nice as well. So happens to be sitting on another path. I think it's from parent directory, you can't quite see on here. But you do now get stripe of your parent directory. So now you actually see 3 extents, because what we're doing here, we're looking at a PFL. So the first extent on here has a count of, where's it now? Here we go, stripe of 1, here we go. So the first file, the file up to 1 megabyte in total in size, will be on this stripe count of 1, and it will be over all OSTs -1, and it'll be on SSDs. The second extent, which is down here, will now increase the stripe count to 8, keep the same stripe size, but will be on, again, the same pool, which is SSDs. Then finally, as you expect this file to grow over time, so now the last one would be stripe counts of 4, same stripe size, we could have increased that. If I get out of the way, down here, see now the last extent on the hard drive. So this gives you, if you have prior knowledge of how your file will grow over time, how you can set this different stripe size, count, size, and also which pool it goes on to, IOPS media, which should preference to IOPS and bandwidth, and media here, which is preference to sequential I/O. And as your normal command, we can do quota command. LFS has also a quota. So you can actually see on here, do LFS quota and give it the path name, which is where Vic resides. And I think you have a user quota and a group quota. You also can apply a quota to a pool as well. So if you have a pool quota, you can specify your pool quota for your SSD, so it's smaller, for example, because you may not want to use this, put all your data on SSDs. So the way to do that is by putting a smaller quota on your SSD and have a larger, wider quota, or a bigger quota on your hard drives. So thank you for your patience. So what I'll will also propose, and if you think about how these things go forward, so this is kind of the basics of purely what is a Lustre, what is a stripe, how to actually use PFL, for example. But there's other topics we could possibly cover going forward, things like best practices, do and don'ts, I/O strategies, how to use middleware applications such as MPI/IO, for example. How to do application profiling using DORSHAN, which should probably kind of probably also end up going into perhaps a workshop where people can actually try out their own applications and run applications and profile live in a classroom environment. We also didn't mention anything at all about how metadata can become parallelized by using this DNE, which is distributed name environment. But it's the same way as OSTs. You parallelize your data using OSTs. You can increase your metadata performance by increase the number of metadata targets. And this framework, DNE, has some different methods to increase your metadata. So all these kind of topics going forward of where we could go with future tutorials. Thank you. Thank you very much. Your strike count. Yes. So one thing I did for important point of stripes I didn't mention is that you can't change your stripe once it's actually being applied. So you set your stripe when it's actually before you run applications. You may then set your strike characteristic to use 2 or 4 OSTs. You run an application, you benchmark it, and get a certain level of performance out. If it's slower, you have to then perhaps delete all that data or write into another directory and then benchmark it again. LFS migrate? Well, oh, you could. That's a more advanced topic, I suppose. But yes, yeah.
Specifically in
So,
it's not a user action. Had a config change that required a write conf. The write conf deletes, it turns out. You pull config. I didn't know that until my NVMe is full of cold data. I'd like to get my NVMe back.
oh, yeah. So the right answer is you can, for existing files, I mean, what was mentioned is if you're just testing out things, you can try again. But if you've already placed all your data, you can use, there's a command, LFS migrate, and then you can specify exactly the same options as LFS set stripe, but you apply it to each of the files, and then it will make a copy. It'll move your data around to the new.
From the user's well, from above the file system's perspective, it doesn't know the blocks are moving around.
Correct. Yeah. I mean, the files, it won't migrate files that are actively being written, but it keeps the same inode numbers and paths and everything like that. It just moves them across to a different OST.
What?
What's different?
Thank you. With lots of different quotas, lots of different pools or stripes, what happens if one of those intermediate quotas fills up, which you kind of feel it's going to happen without the user really noticing? Does it just fall back down onto whatever's left?
So Lustre has a nice way of trying to mitigate against that. So there's a couple of parameters on there, but by default, I think by default, if the difference is less than 20% difference for all the OSTs, as in the usage, it will do round robin. So it will go round robin and hopefully spread the load out. You can also then say, you can change that round robin to a more preferred method to say, if your one OST is very high, like 90%, preferentially skip over that one. So you can then.
Possibly the actual answer to the question is on the quota point, we set a project quota that is not tied to a pool and a pool-specific fast pool quota so that they can only use a tiny amount of the fast pool. And the overall quota is the thing that actually does the massive cap. So you don't end up fighting a quota on the HDD pool as well. Yeah.
Yeah, there's another mechanism as well. I mean, so the pool quotas would prevent one user, from filling up the pool, but it doesn't prevent all of the users. Typically, your quota is oversubscribed for a given, capacity. There's something called a pool spill, which allows you to set up, say, for your flash pool, you can configure to say, if the flash pool is full or above a certain percentage, then any files that are created in the pool would actually go straight to the disk pool, right? And so you'd give it the name of the disk pool, and you can actually supply cascading, so you have a flash 1 pool, a flash 2 pool, this is whatever, carrier pigeon, right? So it gets slower. Yeah. Yeah, your writes would complete, but at a lower performance. And of course, if you have exascaler, there's active, you can have active management of the pools so that it will drain data from one pool into another pool.
Any more questions?